In this part of the PPST, we will look at algebraic reasoning and in order to determine the validity of algebraic statements. The first thing we'll look at is if-then statements. A conditional statement is one that can be put in the form if A then B, where A is that hypothesis and B is the conclusion. Therefore, if we look at the statement, if x and y are integers, which is our hypothesis, we want to know the validity of the conclusion, then x plus y is the same as y plus x. The first thing we will look at is our hypothesis. Looking at the set of integers, if we recall, the integers are our set of positive and negative whole numbers including 0. So our statement says that if we pick any two integers, we want to know if x plus y is the same as y plus x. Through inductive reasoning or picking a few examples, we can see that 2 plus 3 is the same as 3 plus 2, which gives us 5, and both 3 and 2 are integers. If we pick different integers such as 0 and negative 2, we have 0 plus a negative 2. We want to know, is that the same as negative 2 plus 0? And indeed it is. It is negative 2. In order to determine if the statement is true using inductive reasoning, we would have to check an infinite number of examples. But we would notice that this rule is really just the commutative property of addition. Therefore, it is always true. To determine if a statement is false or that it is invalid, we look for a counterexample. For example, if we have the statement if x is positive or greater than 0, then we want to know, is x squared greater than x a valid conclusion? If we only used inductive reasoning and picked on one example, such as 2, we might get the wrong conclusion. 2 squared, which is equal to 4, and we can see that 4 or x squared is indeed greater than x or 2. Again, we need to find one counterexample to show that this statement is invalid. What if we chose x equal to 1/2? If x equals to 1/2, then 1/2 squared is 1/2 times 1/2, which is 1/4. And we want to know, is 1/4 greater than 1/2? And the answer is no, 1/4 is less than 1/2. Therefore, we found our counterexample, which makes this statement false or invalid. We can also look at algebra to draw conclusions. For example, we have this statement, if a divided by 2 is b, I want to know or represent 4a. I can solve this either numerically, using a few examples, or algebraically. If I look at it numerically, I would just select some values of a and determine what happened to b as I went from a divided by 2 to 4a. So for example, if a is equal to 2, then b is given by a divided by 2, or 2 divided by 2, which is 1. Well, now if I want 4 times a, I would go 4 times 2, which is equal to 8. Looking at the relationship of a over 2, which was b, and 4a, which is 8, I can now see that 4a is equivalent to taking the original b of 1 and multiplying it by 8. Likewise, if I look at a is equal to 6, then b is equal to 6 divided by 2, or 3. 4 times a is 4 times 6, which is 24. And if I look at the relationship, 4a is 8 times greater, so it would be 8b. Looking at this algebraically, I could multiply both sides by 2, giving us a is equal to 2 times b. Now I want 4a, so I multiply both sides by 4, and I would see that 4a is indeed equal to 8b.